Hi students. In this lecture, I am going to discuss problems. Let us see first one. Suppose the rod with the balls A and B of the previous problem is clamped at the center in such a way that it can rotate freely about a horizontal axis through the clamp. The system is kept at rest in the horizontal position. You can see previous question means question number 103. See here, two small balls A and B, each of mass m. Rod is light and horizontal. Here in this case, rotation about vertical axis. Okay. So now in this case, we are taking axis is horizontal. It is axis is horizontal. Yeah. System is kept at rest in the horizontal position. A particle P of same mass is dropped from a height h on the ball B. The particle collides with B, sticks to it. Find the angular momentum and the angular speed of the system just after the collision. What should be the minimum value of h so that the system makes a full rotation after the collision? So first make diagram for the given data. So given that rod is horizontal and we can see rod is horizontal, it is now free to rotate about a horizontal axis. That means now this system rotates in vertical plane. You can say this is A and this is B. Now this is axis which is normal to plane of the board and horizontal. Okay. Having masses each m. Suppose length of the rod, it is L. Now we are dropping a body of same mass from a height h. It collides with B and sticks to B. So initially the system AB is at rest. So now we have to calculate what is the angular momentum of the system. See first part, find the angular momentum and angular speed of the system just after the collision. You can see in this system rotates about this axis. So we have to conserve angular momentum about same axis. Let us see now. So first of all, just before making collision velocity, since freely falling, its velocity will be root 2gh. That is called as v naught. That is root 2gh. So now, since rotation is about this axis, we conserve angular momentum about same axis. So separation equal to L by 2. So I'm writing here m v naught into L by 2. This is equal to I omega. And say I value how much? It is 2m. This is m. I value m into L by 2 whole square. So I think we can write directly. So we can take directly here m into square of L by 2 into 3. See why I have taken 3. Mass m, this also m, and this mass also m. So m into square of L by 2. Same thing here also. Total value 3 into m into square of L by 2 I omega. So from this, we are going to get omega value, right? So we got now angular momentum m v naught L by 2. Next omega value. So L by 2 and 1 gets cancelled here. M, M gets cancelled. Omega equal to, see what else left? L by 2 here. So 2 V naught upon 3L, where V naught value root 2ZH. This is omega, right? Now see what we have to calculate. What should be the minimum value of H so that the system makes a full rotation after the collision. So now you have to focus very carefully how to calculate this. Let us make a diagram once again here. So having a 2 point masses, 2 point masses here M, and this is now 2M. Okay. Now system having angular velocity, that is omega, like this. So first we have to focus what is the basic requirement for the system to make a full rotation. Okay. So here what I'm doing is, since it is a rod, when rod becomes vertical, omega becomes 0. We are taking the critical case. That means, let us make a diagram once again. Suppose now rod is becoming vertical. When rod becomes vertical, so we have one possibility that, one possibility, it is B and the other part. Okay. One possibility, A reaching the topmost point and B is now here and rod comes to rest. Second possibility, B will be at the top and A will be at the bottom and omega becomes 0. See here which is now required condition. So one thing is that if I am taking this as now reference level, I am taking the horizontal as now reference level. Then see what we can do here. Let us take this as reference level. Initially, no gravitational potential energy, only kinetic energy. That is equal to half I value 3m square of L by 2 whole square, half I omega square 2 V naught by 3L. This is equal to, this is equal to, now see what we can say. If B reaches topmost point and omega becomes 0, just observe carefully. Suppose B is now at topmost point and omega is 0, means rod is now stationary. If we just push B, just push it, see what happens. Again, B reaches topmost point. This is what we can say depending on conservation of mechanical energy. I am repeating. If B is now at topmost point, if we just push it, again B comes to same position according to conservation of mechanical energy. But if you observe, if A is now at topmost point and rod is stationary, if you just push it, again A cannot reach topmost point. Narration is A has mass m and here mass is 2m. Okay. That means if you just push it A, this point B cannot reach topmost point. Okay. But if you take B is now at topmost point, if you just push it, B can reach again topmost point. That means the basic requirement is when B reaches topmost point, omega becomes zero. This is the minimum requirement. This is the minimum requirement. Okay. So I'm writing here loss in the rotational kinetic energy converts into gain in the potential energy. That means 2m. You can see from this reference level, B moving up by a height L by 2, A comes down by a distance L by 2. That means B gaining gravitational potential energy 2m into G into L by 2. A losing gravitational potential energy, so m into G into L by 2. So remaining just calculation part. Now simplify and see what we are going to get. So here 2 mgl by 2 mgl by 2. So I'm writing here first of all, both sides mass gets cancelled, right? Next G, here 2 and 2 gets cancelled, GL and GL by 2. Remaining is now GL by 2. See carefully, GL minus GL by 2. So GL by 2 is left. Coming to left side, see what is left here. L square gets cancelled. 2 square gets cancelled. Here 3 square 9. This is 3 is there. So 9. This is now 3. So remaining is now what else left here? V naught square. V naught square means it is 2GH. Okay. V naught square 2GH. Remaining is 3 here and this is 2. 2 here. 3 square 9. And this is now 3. Remaining 3 left here. Okay. So 2 gets cancelled. That is equal to GL by 2. G and G gets cancelled. So H equal to 3L by 2. Cross check 3L by 2. That is our final answer. Okay. So basic thing is that here is A reaching topmost point or B reaching topmost point. So when B reaches topmost point and when B reaches topmost point, omega becomes 0. That is the minimum requirement. Okay. Let us see next one. Right. See the question given. A thin spherical shell of radius r lying on a rough horizontal surface is hit sharply and horizontally by a cube. Where should it be hit so that the shell does not slip on the surface? Given it is a hemispherical shell, sorry, thin spherical shell. Right, at what height we have to hit? Does not slip. Does not slip means it rolls without slipping. Okay. Let us see. It is now thin spherical shell. It is a hit at some height. Let us take at some height above center. So hitting sharply means providing or an impulse is given, okay, at some height above center. Then see what happens. Condition given that it rolls. Okay, so no slipping. So first of all, we can write condition here. Net impulse equal to change in momentum. That is m into VCM minus 0. Initially, velocity was 0. So first thing, J equal to M into VC. Now I am taking here, let us take conservation of angular momentum about the contact point, because rolling can be taken as pure rotation about contact point, right? Then see what I can write. J into distance equal to R plus H. That is R plus H. This is equal to I into omega. About the contact point, we can see about this axis, moment of inertia. It is, see how much this is parallel to diameter of the shell, means about a tangent. It is now 5 by 3 mr square about a tangent, 5 by 3 mr square into omega. Right? And see in the place of omega what we can write. So in the place of J, I am writing M into VCM. This is R plus H, and that is equal to 5 by 3 mr square. In the place of omega, I am writing VCM by R because no slipping. So I'm writing here VCM upon R. Now see what happens. M VCM gets cancelled. 1 R gets cancelled. R plus H. R plus H is equal to 5R upon 3. That means H equal to 5 by 3 minus 1, 2 by 3. 2 by 3 R. So at a height 2R by 3 from center, means above center, if you provide an impulse, it starts rolling without slipping. Or if you remember, almost same kind of question we have solved. At which point we have to apply force so that frictional force will be zero. Means in this problem, if question is like at what height force must be applied so that frictional force on the body will be zero. Answer same. Okay. Since no friction here, no impulse because of friction, right? Okay. Let us see next problem. Let's see the question given. Figure shows a rough track, a portion of which is in the form of a cylinder of radius r. Diagram is given. With what minimum linear speed should sphere of radius small r be set rolling on the horizontal part so that it completely goes round the circle on the cylindrical part. Okay, this is a small sphere. This is now cylindrical shape, and basic condition is completely goes around the circle in cylindrical part. Let us say how we start the problem. So it has to complete now vertical circle, and given sphere here. This is now rolling. Velocity ticket as V naught, which we have to calculate. It is now rolling without slip. So if you remember while discussing vertical circle, the basic condition is the sphere should not lose contact. Okay. If you are taking the limiting condition, assume that when we are providing minimum speed on reaching topmost point, it just loses contact. Okay. So if it is losing contact, the only force acting on the sphere is now gravitational force, which is vertically down. Now see carefully. This gravitational force provides now centripetal force. So I'm writing here mg is providing centripetal force which is equal to m into vc square by r minus r, because this is small r and this is capital R. Center of the sphere follows circular path of radius r minus r. This is one condition. Now I am taking here conservation of mechanical energy. Let us see. At the bottom, total energy. At the top, total energy. At the bottom, half m v naught square into 1 plus beta. That is 1 plus 2 by 5, 7 by 5. This is equal to on reaching topmost point, potential energy is there. It is m into g into 2 into r minus r. You can see height from center to center, r minus r. Again, r minus r. So 2 into r minus r plus, because of, you can see here kinetic energy, once again half m vc square. What is vc here? It is speed of center of mass. Okay. We are focusing center of the sphere, right? Into 1 plus 2 by 5. That is 7 by 5. Now remaining just calculation part. What we can do is in the place of m vc square, substitute mg into r minus r, half m v naught square into 7 by 5. That is equal to, in the place of m vc square, right, mg into r minus r. mg into r minus r. Then see what we get. This is 7 by 10. 7 by 10 plus 2. 7 by 10 plus 20 plus 727 upon 10. Okay. So 27 upon 10 into mg into r minus r. Okay. Right. Mass gets cancelled. 2 5 10. 10 gets cancelled. V naught is equal to 27 upon 7 into G into R minus R. Right? So first thing we are focusing when we are providing minimum speed, it is just about to lose a contact on reaching topmost. So only gravitational force provides centripetal force. So next, writing energy equation. Okay. Let us see the last question. A uniform thin rod of mass m and length L is standing on a smooth horizontal surface. A slight disturbance causes the lower end to slip on the smooth surface and the rod starts falling. Find the velocity of center of mass of the rod at the instant when it makes an angle theta with the horizon. So we have to find velocity of center of mass. Let us see. Okay. So condition given that initially rod was vertical on a smooth horizontal surface, it is vertical. If you provide a slight disturbance, okay, if you slightly push it, then see what happens. In this, if you observe forces acting on the rod, one is normal reaction from ground and other one is gravity. Since both are acting along vertical, center of the rod follows only straight line path, because initially for center of mass velocity is 0. net force only along vertical because normal reaction occurs mg downwards. That means center of the rod follows now only straight line path. It is vertically down. Okay. After some time, suppose rod is now like this. So rod makes an angle theta with a horizontal. It makes angle theta with a horizontal. This is now center of mass. You can see rod is neither in pure rotation nor in pure translation. It is a combination of both. Okay. So now what we can do is, if you observe for the contact point velocity, it is like this, right side. And for center of mass velocity, vertically down, right? If you draw normals for these velocities, okay, draw normals for these velocities, they will intersect at axis of rotation. So now you can see. So now you can see at this instant, rod is in pure rotation about this axis. Imagine this board plane. Axis is now normal to the board and horizontal. At this instant, this is axis of rotation. That means this is instantaneous axis of rotation. About this point, this rod is in pure rotation. Now see what I can say. Since it is given smooth surface, there is no energy loss. Since center of mass coming down, there is a loss in gravitational potential energy. Initially height was L by 2. Now height is, suppose I'm taking this is A, this is B, this is C, and this is D. We can see the length BD is L by 2 and length of AD is L by 2 sine theta. So present length is L by 2 sine theta. Initially length was L by 2. That means loss in gravitational potential energy is mg L by 2 into 1 minus sine theta. This is loss in gravitational potential energy. This loss converts into kinetic energy. Since we are taking pure rotation about this axis, half I omega square. While taking I value, we should be very careful. Now we are taking I value about this axis. Okay. If you see axis passing through center of the rod, that is ml square by 12, right? Ml square by 12. But we want about this axis. So now we have to use parallax theorem, right? Now use a parallax theorem here. This axis is a parallel to its own axis. Distance equal to L by 2 cos theta. So m into square of L by 2 cos theta. This is I value about this axis. Half 5 omega square. Now solving this, we are going to get omega value, right? Now we want to calculate velocity of center of mass. So once omega is known, you can see VCM equal. Since rod follows pure rotation about this axis, distance of center of mass from axis of rotation L by 2 cos theta. That means VCM is equal to R omega, R value L by 2 cos theta, R omega, right? So we are using the concept of instantaneous axis of rotation. Once omega is known for any point, velocity equal to omega into distance of that point from axis of rotation. That is what I have taken here, L by 2 cos theta. Distance of center of mass from axis of rotation into omega, right? So remain just calculation part. So I hope you got clarity.